Welcome to Calculus. Today we will investigate how to find position, velocity, and acceleration by integration. We'll take a look at two examples. Our task here is twofold. We want to find the position, velocity, and acceleration functions for given values of t, and then we want to graph all three of those functions. So what we're given for our first example is the velocity function, v of t equals 2t minus 15. And we also know a little information that's initial conditions. I know that the starting value of, or the initial position when time is 0, s at 0 is 50. And then once I gather all three of those functions, I really want to calculate what is their value when the time equals to 4. So what we should do first is just identify what are our three functions. So I know that the velocity function, it's really going to come in the middle of the three. And so my velocity function here, I'll place it kind of centrally. V of t equals 2t minus 15. That's a nice linear function. And I could go ahead and graph that. I see my middle graph here is designated the velocity function graph. So I see that 2t minus 15, that's a line with the y-intercept negative 15. And if I look for the x-intercept by plugging in 0 for the y value and solve for t, I'm going to get t equals, if I add 15 over and divide by 2, positive 7.5. So that's going to give me a second point here. If I graph that, 7.5, and extend my line, I've got my velocity function and its graph. For acceleration, we can choose that one because that's probably the next easiest function to find. Of course, velocity was just given to us, but acceleration is basically the derivative of velocity. So I'll notate that here, a of t is equal to v prime of t. So in terms of a function, that's going to be just the derivative of 2t minus 15, which is just 2. And I can really easily graph that. That's a constant acceleration. And that really takes care of my graphs for my velocity and my acceleration. Now, to get to position, what I've got to do is really find the antiderivative or the integral of my velocity function. So position, typically we call that s of t. And that is the integration of my velocity function v of t dt. So we'll set that up. That's the integration of 2t minus 15 dt. And what that's going to give us is 2 times 1/2 t squared minus 15t. And then because this is indefinite, I need to put plus c there. So for me to be able to graph a particular solution here for my position function, I really need to use this initial conditions. The position at time 0 is 50. So I can simplify this down a little bit more. 2 times half is just 1. So really the function is t squared minus 15t plus c. So then we're going to take and say that, hey, when t is 0, the whole function equals 50. So 50 equals 0 squared minus 15 times 0 plus c. And those zeros are going to cancel out. So we see c as exactly equal to 50. So my function for position is going to be s of t. And this is where the integration comes into play, equals t squared minus 15t plus 50. So I can tell by that square on my time that that is a quadratic function. And so I want to graph it. Probably the easiest thing for me to do is to get a calculator to help me generate a table of values. So what I'm going to do is I'm going to jump over to the calculator and I'm going to choose the graph screen. I just want to enter that function that we just found through integration for position. So that's going to be, again, t squared. And what I'll do, since I'm here on the calculator, I see that it's defined in terms of x. I'm going to translate my t's to be x's. So x squared minus 15x plus 50. So graphing it gives me a nice view of this position function. And what I'd like to do is get a table of values. So I see on my graph that heads out all the way to 16, it looks like. So I do also want to kind of adjust my window. So I'm going to go here to window zoom, and I'm just going to select window settings. So for my X minimum, I'm going to put 0. And again, we want to go out to 16. We'll go for a Y minimum of negative 200 and then a Y max of positive 200. We'll see how that gives our graph. So that kind of gives us a more elongated view, and the parabola is much more flat, but we can still see the quadratic nature. So I want to get a table. So again, I'm going to menu 7, and I'll use the split screen one. And this I want to just record. So I'm starting at 0. So I see the X value at 0 is 50. 1 is 36, 2 is 24, 3 is 14, 4 is 6. So that's all descending. That's that left side. The x-intercept, or at least one of them, is at 5, 0. 6, negative 4, 7, negative 6, 8, negative 6. So it looks like our vertex, the minimum of this quadratic, is right between 7 and 8, because I see that the y values are duplicated. Probably at 7.5, right where we had the x-intercept for our velocity function when we graphed it. So then I can see that quadratic pattern. It starts to climb back. So from negative 6 to negative 4 to 0, 6, 14, 24. These are values we've seen already, just in reverse. And at 16, we're at 66. So what I've done is I've copied that table down. And let's take this back to our notes so that we can graph it. So what I'll do is I'm just going to write that table. There's not a lot of room here. So what I'm going to do is I'm just going to graph it from the table that I had recorded. So I've got here 0, 50. At 1, the value is 36. So I've got to estimate here. I'll just estimate that that's about 36. 2 is at 24. So right under 25 there. At 3, the value is 14. At 4, it's 6. And I see that I need that actually t equals 4. So I'm going to write s at 4 equals 6 here, just so we grab our value. At 5, it's at 0. At 6, we have the value negative 4. 7's negative 6. And then here's our vertex right there at 7.5. And then it starts to climb back again. So at 10, we've got another 0. And at 11, so I'm starting to see that this is just very symmetrical. 6, 12 is 14, 13 is 24. 14 is 36, 15 is 50, and 16 is 66. So that did take a little more because we had to get a table. But once we've grabbed the points, we can really handily graph that position function. So we see a nice relationship here between position, velocity, and acceleration. The position is a quadratic. Velocity is a linear function that has a slant to it. Acceleration is a constant linear function, perfectly flat. So my last task here is just to say, what's the value of the function at 4? We found that at the position function at 4 is 6. The velocity function, we could probably just plug 4 in real easily. So it's 2 times 4. So that's 8 minus 15. And that's going to be negative 7. And then for acceleration, it's the same value everywhere. So a at 4 is 2, just like a at anywhere else. And that completes our task there. Again, what we've done is we use differentiation integration to come up with our functions, our equations, and we just graph the equations. A couple of those we could just graph using algebraic strategies. One of them we graphed with a calculator, and then just grabbed the values of the functions at 4. Let's take a look at our second example. So our second example starts with acceleration. So at this point, we have a good feeling about where different items go. So acceleration, we know, is in a way, the third or the final descriptor of this motion. So it's given here as negative 12t squared plus 84t. So it's a little different. This acceleration function, this is a quadratic. So as I go from acceleration, I know that the next function I can find is velocity, since that's the second or the middle function there. And it's the integration of acceleration. So if I'm going to integrate the acceleration, it's going to be negative 12 times 1/3 t cubed plus 84 times half t squared plus c. I always have that constant. So then when I simplify here, that's going to be negative 4t cubed plus 42t squared plus c. And then I need to find the value of that c, just as in the last one. But I'm kind of helped out here. I'm told that the initial conditions for velocity at 0 is 0 position. So if I were to plug in zeros for these t's, those other terms like the negative 4 and the 42 would cancel out. And I just end up with c equals 0. So it turns out c has no value at all here. And my velocity function is going to be given as negative 4t cubed plus 42t squared. And that is that. So I'm going to start highlighting our functions we're generating here. So there's the velocity function. And we had, again, already had the acceleration function. So I'll highlight that. So all that's left for us to find in terms of equations is the position function. So again, that one's in a way the first of the three. Position is the kind of the first description of motion. And that again is going to be the integration, but now it's going to be integration of my velocity function. If you think of it, it's the second integration of acceleration. So again, we'll integrate this velocity. So that's going to be negative 4 times 1/4 t to the power of 4 plus 42 times 1/3 t to the power of 3 plus c. So for us, that's going to reduce down to negative t to the power of 4. And then 42 divided by 3 is going to give us 14 t cubed. And I've got the plus c. So I'm going back to my information. My initial conditions for position are just the same as velocity. Position at 0 is also 0. I plug in 0 for these t's, it's going to just leave c. So c equals 0. And like with our velocity function, there is no constant term there. So we'll write here s of t is just negative t to the power of 4 plus 14t cubed. And that completes our work just finding the functions, finding the equations of position, velocity, and acceleration. Again, here we were given acceleration, so we integrated twice to get velocity and position. So now again, we would like to graph those. So what I want to do is again employ the calculator, because I can see here my functions are a lot more complicated acceleration is nowhere near being constant. It's the quadratic. So velocity is a cubic function and position's a quartic function. So a lot of arithmetic if I were to try to do that by hand. So I'm going to come over to the calculator and let's open a new graph. And what I want to do is just graph all three on the same plane. So I'm going to start off with our position function first. So again, I'm going to translate t's to be x's so that it fits in with the notation here in the calculator. So it's negative x to the power of 4 plus 14x to the power of 3. And we'll graph that one. So there I can definitely see that's definitely a quartic function. So at this point, I'm looking at it and it kind of doesn't look like it's a quartic function. It looks cubic, but I got to keep in mind that this is very much zoomed in. So I'm just going to investigate a bit. I'm going to hit menu. And what I want to do is just resize my window so I can see the rest of this function. So I'm going to just hit window settings. And what I'll use are the dimensions of my graph like we did on our first example. So from 0 to 16 will be good for our x values. I want to adjust my y minimum and maximum. So I'm going to give a great deal of room here. Let's go to 6,000, negative 6,000, all the way to positive 6,000. So we can see the graph clearly. And with that, I can see, okay, this is really a quartic function. It's got two arms that descend towards infinity on the left and the right. And that gives me a good opportunity to input my other two functions. So I'm going to again hit menu and I want to enter a graph. And here let's put our velocity function. So that one's negative 4x to the power of 3 plus 42x squared. And just placing that here, I can definitely see that's in a way the right side of a cubic function. And let's put our last function in. By the way, it looks like that x-intercept there would correspond with the maximum of that position function, which kind of goes with what we know about functions and their derivatives. So let's get in the last function here, which is the acceleration function. So it's the quadratic, and it's negative 12x squared plus 84x. And we can kind of get a clear view of that quadratic. So again, its x-intercept is going to be the maximum value of the velocity. So all that to say, I want to graph these on our screen. Let me get a table. So here I'm going to get a split screen. And what I'm going to do is I want to record all three values. So for the first entry here, which was our acceleration, I got 0, 0. See, climbing up. So I'm going to record all these y values all the way up to 16. I definitely see that I've got a maximum value near there at about 10. And then at 16, it's descending quickly to really large negative values. Switching over to the velocity function. Again, I'm going to head back to not that far. Let's go to 0. Again, it starts at 0. Remember, our initial conditions were 0 for all these functions. And then it rises. Looks like it attains a maximum somewhere around 7. Descends, descends, descends. And like the other function, descends to large values of y as x heads to the right. And then our third function, the position one, that's the quadratic. So what we see here is that it's got a vertex somewhere between 3 and 4. I see the repeated values there, 144, 144. and then it also decreases strongly to the right. So I'm going to record all those values 0 through 16, and I'm going to head back to the graph to record that on the coordinate planes that we've got here. So we'll start with our acceleration function first. So its values are going to be from 0 at 1 at 72. In fact, what I want to do is just catch some of these key values. So 2 is 120. In fact, let me graph this. I'm graphing this one on the position, and that scale is way big. I was wondering why it wasn't fitting in. So there's our acceleration. So 0, 0, 1 is at 72. So about 3/4 up there. 2 is at 120. And I see here I need to calculate t equals 2. So I'm just going to write here a at 2 equals 120. That was from the table. And then we can graph the rest. 3 is 144. So is 4. So there's the vertex there in between 3 and 4. So it's likely to be 3.5. 5 continues back down with this same trend. So at 7, I've got a 0. 8 is negative 96, so almost there at negative 100. 9 is negative 216. 10, negative 360. 11 is negative 528. And 12 is off my graph at negative 720. So we'll let that suffice for the acceleration function. Again, this was the one we were given at the outset, at the start. Definitely a nice parabola, nice quadratic. So that right side we can see, left side would continue down if we were to graph it. All right, so let's graph the velocity function here. So that's the middle one. Again, I'm just pulling values from what we saw on the calculator view. So there's 0, 0. 2 is, or I'm sorry, 1 is 38. So it's not a huge rise here. 2 is 136. So I'm going to write here v at 2 equals 136. At 3, this function starts to grow. 270. 4 is 416. 5 is 550. 6 is 648. 7 is 686, and 8 comes back down to 640. 9 has the value of 486. 10 is 200 exactly. 11 is negative 242, so we decrease there. 12 is going to decrease even more, negative 864. 13 is negative 1690, so it really starts to decrease here. 14 is negative 2,744, so off the graph. And that's going to be this cubic function. So we're seeing in a way that the right side, the left side we're not seeing, but it would go up. And our last function here is going to be this position function. So our last one that we found, it's the quartic function. So again, I'm just going to graph from the values that we took from the calculator. So there's 0, 0. At 1 here, it's 13, so it doesn't rise much. 3 is 90, or 2 is 96. So I'm going to write here position at 2 equals 96. And again, that was a value I just grabbed from the calculator table. At 3, it has the value of 297, so it does start to rise here. 4 is 640. 5 is 1,125. 6 is 1,728. So getting closer to this 2000 mark. 7 is above that at 2,401. And 8 is 3,072. 9 is 3,645. 10 is given as 4,000 exactly. 11 is 3,099. So it starts to drop again. That's a maximum there. It looks at 10. At 12, we've got 3,456. At 13, it's 2,197. 14 is as 0. 15 is at negative 3,375. And then 16 is negative 8,192. So we'll graph this one, and we're seeing again the right side of a quartic function. And definitely, if you remember that left side that we saw in the calculator, if we were to continue, both sides would go down. And that completes that second example. So kind of using the calculator heavily on this example to get our table values so that we could graph. And also makes it quite easy to grab different values for position, velocity, and acceleration at a certain time value. Well, thank you for joining for these two examples of finding position, velocity, and acceleration by integration. See you soon.